Okay, welcome back everybody. I'm just about ready to start. I believe this is my fifth video on building MakeMore using C. I'm basically just following Andrej Karpathy's videos and trying to learn a little bit about AI, how it works, and so today I'm going to be talking about the GPT tokenizer. So let's just take a look at what that's all about. Basically, the tokenizer's the front end of the AI system, where we break down the input into tokens, into pieces of text or integers or whatever you want. Years ago, when I started programming, I always thought that tokenization meant breaking sentences up into words, and the words would be delimited by punctuation, such as commas or periods, exclamation marks, and things like that. But apparently, with the tokenizer used by ChatGPT, just breaks the input up into pieces that to a human just look kind of random. So it breaks the text up into random chunks, and then each one of those random chunks is assigned a number, and all of those numbers make up the input. So what we're going to do today, we're going to start with what's called byte encoding. Byte encoding is just reading each character as a simple 1-byte integer, and this in the C language, this is really easy. Our alphabet will consist of all the unique bytes. So that'll be our alphabet. And this is exactly what we've done with the names file we used up to this point. Our lookup table will be the size of our alphabet by the dimensions. So let's say, for example, that your alphabet was just the 26 lowercase letters of the English language, and the dimensions were 10, then your lookup table would be 26 by 10. Now we can increase the alphabet by using a technique called Byte Pair encoding. And the way Byte Pair encoding works is we count consecutive byte pairs, and we want to look for the most common byte pair. And once we find the most common byte pair in our input, we can then replace that byte pair with a single byte. So instead of having 2 bytes, we'll replace it with 1 byte. So what that means is that our input will become smaller because we're replacing 2 bytes with 1. But our alphabet will grow by 1, making our input table larger. And of course, we repeat this a number of times. And each time we do this, we call that a merge. And we have to keep track of these merges, because later on we'll have to undo it to continue using our AI system. So let's take a look. I think what I'll do is I'll just do an example with using my tablet here, so I can write an example. We'll see how it works. Kind of an ad hoc try here, so it may or may not work, but let's take a look. Let's take an input, just simple letters like, for example, 2B or not to B. Let's say that's our entire input. If you look at our input, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 18 bytes is our input. Now if you look at every 2 characters, which 2 characters occur most often? Well, remember also that a space here is a character. So we have to look at this input, including spaces and punctuation and all this kind of stuff. So if we look at the word, just the pair TO, well, that occurs once here and once here. So this byte pair occurs twice. But if we look at, for example, I don't know which another example would be. We could look at, let's take a look at this. I don't even think we can get, well, let's say O space here. An O followed by a space. Well, that occurs here. And then an O followed by a space occurs over here. So an O with a space also occurs twice. Now I'm not sure if any other, if there's any other duplicate matches here, because again I'm just doing this off the cuff just to see if it works. So space B. Oh, there's also a space B. If you look at, there's a space B. So that's like a space in the letter B. And that occurs space B and a space B over here. So that also occurs twice. Now I don't see any in here that occurs 3 times, but that's fine. Anyway, this string is going to be converted to bytes. And if you look at the ASCII table, let me show you the ASCII table here. I'll just go in here and I'll say man ASCII. And if we go to, let's say the letter T here, the letter T is 116. So the value is 116. So that means that, let me move this guy out of the way here. So this would be encoded as 116. And then the O here, if you look at the letter O, would be 111. Okay, so we encode the letter O as a 111. Just taking the byte values for each one of these. And then a space, of course, is going to be 32. So the next one will be 32. And so on. So we just do this encoding just by reading byte for byte, or byte by byte. And the way byte pairing works, so what we're going to do is we're going to find that this pair here, TO, occurs 2 times. We can just mark it right here. So you have a TO here and a TO here. Occurs twice. What we want to do is we want to replace that with the next highest value. Well, if you look in our string here, what's the largest letter we're using, which is probably a T. QRST. I think a T is the highest value. So, which means this is our highest value here. Is once in our input, that's the highest value. So what we want to do is we want to take this TO and we want to replace it with the next highest value, which will be 117. So basically our new string, our new input, will be, instead of doing 116 followed by 111, we're going to replace that with 117. Okay, and we're going to do that 2 times. So what's going to happen then is our input then will be 18 minus 2 is 16 bytes long. In other words, our input got shortened by 2 bytes because that TO occurred twice and we replaced it with a 117. Okay. So that's basically the idea behind this byte pair encoding. And what I've done here is just one merge. Okay, so, and we can do this over and over and over and over again, and little by little our input will become shortened and our alphabet will grow. In this example here, our alphabet, I don't know how many unique characters our alphabet is equal to the list of unique characters. So I can't count them up here. We've probably got about 5 or 6 unique characters here. But since we're adding in a new code here, it means our alphabet increases by 1. The alphabet increases by 1 with each merge. Now that's kind of the general idea of what's going on. Let's look at some of the code and see if we can figure out exactly how this is working. Okay, so let's take a look at some code here. So I have here code, and the first thing I just want to look at is our parameters we're using for this example. The file I'm using is called shakespeare.txt, and the reason I'm using this is because I've looked at the file and it's basically just an ASCII file. So, which means the characters are all like 0 to 127 or something like that. So I don't have to worry about Unicode, which means I can kind of ignore the whole idea of UTF-8 or 1632. I can ignore all that because I'm just going to be working with pure ASCII in this case. My block size is going to be 3, so that's the size of my bigram, 1 bigram. My batch size is going to be 32. I'm going to be bringing in 32 bigrams at a time. Dimension is going to be 10. And I'm going to go for 600 merges. I'm going to try to do 600 merges, and if you think about it, what that means is that my alphabet should grow by 600, which means I am really, really increasing the size of my lookup table, because my lookup table is the alphabet, number of rows is the size of the alphabet by the dimensions. So every time I do one merge, my alphabet grows by 1, because I'm basically introducing a new byte, a new code. My input nodes are going to be block size 3 times dimensions, which is going to be 30. Hidden nodes, I just have one layer in my example here, which is really trivial. In fact, more than trivial, less than trivial, I guess. I don't know. Bias 1 is 300. My initial learning rate is going to be 0.1. My momentum for calculating the the or normalization, for doing normalization. And then of course I have my gain and bias vectors, and epsilon I set to 0. So these are the parameters I'm using. Now if you look at the code here, the way I start here is to say, okay, the number of raw bytes is from the file name is Shakespeare. So I get the number of bytes in the file. And then what I do is I extract all those bytes and I read them in as integers. So basically, raw bytes here is now just going to be a list of integers from that file. And I also print out the number of raw bytes, how many bytes did I read. And then what I do is I want to calculate my alphabet. So there's my length of my alphabet is 0, but my alphabet now is computed from all the raw bytes. And remember what the alphabet is. It's just basically a list of all of the unique bytes in my file. Like how many different bytes do I have in the file? That's the length of my alphabet. In my example here, I think I start off, I think the Shakespeare text file has 65 unique bytes. That's just what it came out to. I don't, that's including all the upper and lowercase letters it uses, plus some punctuation and things like that. So the initial length of the alphabet, I think it's going to be 65. And I'll show you that. And then I even print out the alphabet here, the initial value of the alphabet. And then what I do is, now that I know what my alphabet is, I want to find the next highest value in the alphabet. So let's say my alphabet has the bytes, let's say from 10 to 100. If from 10 to 100, then the next highest value would be 101, and that's going to be my new value after I do a merge. One thing you have to realize is when you do merges, you're going to have to keep a history of the merges, because eventually after you do your training, you're going to have to undo all those merges, because remember what you're doing is you're training on on an alphabet that you just made up, a large alphabet with and the data is a lot shorter, and so you do all the training on that. But once the training is finished, then you have to go through and undo all those merges. And so now I have a loop here where I'm doing the merges, and I'm doing 600 merges. So I'm going to do this loop here 600 times. And so this brings back the new length of my alphabet. And I just go through getting a byte pair. So if I look at the code here for getting a byte pair, I think I have that in bytepair.c. So I can say get byte pair. Right here is the code for getting a byte pair. It says get the most frequent pair of bytes, integers in the line. So what I do is I just make a square array of length alpha. So let's say my alphabet is 65. So basically what I'm doing is I'm just making a 65 by 65 array, and then I'm just filling that array with counts of byte pairs. So the way it looks is, I guess I could show you on here. Another example would be like this. So if I make an array of 65 by 65, and then what I do is I just read in all the data looking for byte pairs. So for example, suppose I had here let's say this was let's say the letter T followed by the letter O. So T followed by an O. So this number in here would be the number of T followed by an O. So I just count them up. So then I can go through this little table and I can find out which one has the highest count. So once I make this table, I just find out which one has the highest count, and that's the one I use. Okay, so let's take a look. So I go through this, and you can see that what I do here in my loop is I have my history file here. So I put in here, and I is 0. So in my very first merge, I'm putting in the number of pairs I'm finding, the next value I want to use to replace those pairs, and here is the pair, alphabet at N1 and alphabet at N2. So these two numbers here are my pair, and the number of pairs I'm finding. Okay. So what's happening is the number of raw bytes, you see that my file is actually decreasing in size by the number of pairs. So if I find like 10 pairs of the, let's say TO occurs 10 times, then I have to replace that TO 10 times with a single integer. So the number of raw bytes decreases by 10. Okay, and I have to update the raw bytes. So I end up with a new input basically. And the new input is now shorter by 10 bytes than the old input. Okay. And then what I do is I go through and I do the next merge. So the next merge, I is equal to 1. And now I go through the new raw bytes. And I find another pair that's the highest. And then I update my alphabet. I update my input raw bytes. So in other words, my alphabet is growing, my input is shrinking, and I just keep doing this 600 times. Of course, there's a possibility that I don't find any more duplicates. Well, that's fine too. Okay, so after we've gone through those 600 merges, then I can say, well, the length of my alphabet after merging, it should be 600 plus 65, because my alphabet initially was 65, and now I go to 665. And the number of raw bytes, of course, should be a lot less. So let's take a look at, I think I have the output of this particular run. Let me take a look at that for you. Where do I have that? Results here. So if we take a look at, this was my original length of my input. So this is basically here 1,115,349 bytes. That's the length of the Shakespeare file. And the initial length of my alphabet is 65. So what's that telling me, once again, is that I have 65 unique characters inside this file. And here they are. These are the 65 unique characters. And remember the T, I believe, was let's see, an O was 111. An O, P, Q, R, S, and I think a T was 116, and an O was 111. And 122, by the way, is a lowercase z in just the ASCII code for lowercase z. So my alphabet here goes from character 10. Character 10, by the way, is a new line, and 32 is a space. Okay. So this is my alphabet, 65 unique characters. But you notice that 122 is my highest integer value. What that means is after I do one merge, I want to create a new byte of 123. So here I do my merging, 600 merges, And after the merging, my alphabet is now 665. And you can see that after 122, the next byte I created was 123. Then I went to 124, 125. Every time I found a new byte pair, I assigned it a new value and I updated the input file. So I have that. And then you can see now the number of raw bytes is 459,000, considering that I started off with 1,000,000 bytes in the file. And after doing all that merging, I ended up with 459 bytes. And my dimensions here are 10, that hasn't changed. Block size, which is basically the size of 1 bigram. And so our lookup table is going to be 665 by 10. And that's, like for me, that's a big lookup table. And so the size of our input is going to be 30. All these other parameters are the same. Now you notice the number of parameters here is 216,000. If I go down here, where do I see the number of parameters? Right here, the number of parameters is basically just adding up all of these block size times dimension times hidden nodes plus bias 1 plus the hidden nodes times length of alpha plus length of alpha plus dimensions times length of alpha plus bn gain and bn bias. So that becomes my number of parameters I'm using. And if you look at here, the number of parameters, 216,000. Well, 216,000 is really practically 0 parameters. I mean, it's not really very much. Let's ask how many parameter how many parameters in ChatGPT-3. So ChatGPT-3 has 175 billion parameters. ChatGPT-4, 100 trillion. It just seems like it's like, to me, it's mind-boggling. These parameters. It's almost like when you start talking about the size of the universe, like how many stars are in the galaxy, how many galaxies are in the universe. These numbers just go beyond, I think, what humans kind of can grasp or understand. So anyway, GPT-3 is 175 billion parameters. That's absolutely insane. And I have 200,000 parameters. Okay, well, that's about it. And if you look at as I run through, well, just before I do that, let's go through the code here a little bit more. After I do the merging here, I encode the data. And then what I want to do is I want to create the bigrams. So X, this is the input bigram, and Y is the expected output. I encode all of these into these arrays here. I print out the dimensions, the block size. I create our initial lookup table, which is random. And it's going to be, our lookup table is going to be 665 by 10. 665 rows by 10 columns. And that'll be our initial lookup table. And remember, the lookup table is used for embedding. We are embedding, we're creating a bunch of vectors to, I think they call that the attention mechanism. We're trying to get tokens that relate to each other have very similar vectors inside the lookup table, if that makes any sense. I'm puzzled by all this stuff myself, and remember, I'm just a beginner, so I'm trying to figure this out. Chances are I made a million mistakes, but let's move forward. So I create bias 1, I create our weight table here, weight 1, weight 2, bias 2, our gain vector, bias vector. I also leave room for running mean and running variable variance, which we need for normalization. And then I print out the number of parameters here. And then basically what I do is I go into my kind of learning loop. I do 200,000 passes. My initial learning rate is going to be 0.1, but I changed halfway through my learning here. I changed it to 0.01, so I go a little bit lower by a factor of 10. I get a mini batch here, which is going to be 32 bigrams, and I embed them into the embedding table. And then I go through my first layer here, like y equals mx plus b. Basically, that's what I'm doing here. I add the BIOS, and then I normalize to get the normalized layer. And I just go through and compute all of this until I get down to the logits. And I use cross entropy here to compute my loss. And I print out the loss. And if you look at my output here, my initial loss here is 7.85. It's my initial loss. And so 7.85 is my first loss. And then I go through tons and tons and tons of back propagation with all of those partial derivatives and using that chain rule. So tons of matrix multiplication here, matrix addition, just basically working with a lot of linear algebra. Go through all of that until I finally get my gradients, and I can then I can update my W2 gradients, my B2 gradients, W1 gradients, B1 gradients, my excuse me, my lookup table gradients, my bias vector and my gain vector gradients. So I update all of those, and then I free all of those gradients, and I go right back up to the top here, and then I do this loop is 2 or 1, and I do that 200,000 times, and basically just working out. My whole point here is to work out what my new weights and biases are going to be and what my lookup table is going to be. So my lookup table should be getting learning more and more and more by using that embedding business, and so I end up with this kind of situation where my loss goes from 7.85. Well, doesn't seem like it's really made much progress. It goes down to 6.0. And again, I'm not, and the reason is because I don't really have any kind of tuning involved. I'm just using very primitive normalization with very primitive weights and biases. So, and I only have that one layer, whereas Andrej goes into multi-layer situations where you end up with a lot, way more parameters than I have. And you notice this little run took 38 minutes on my machine. So 38 minutes, 6 seconds to kind of do that. But that's basically the idea behind taking the input and breaking it into bytes, and then finding these byte pairs and replacing each byte pair with a new integer value, doing all the merging here. Okay, so I have some of the functions I wrote here: get byte pair. I think I also have here update the alphabet, update the line, and then I have a function here to undo the history, which I haven't used in here because I don't really need it. Actually, I have two functions to undo history, and I have undo history 1. I think undo history 1 works better than the other. Basically, what you're doing with the undoing the history is you go backwards through the history, expanding each byte pair. So I have the history file here that goes 0 to 599 rows. So you start with row 599 and you undo that value. So now your new line will grow. So after you undo all your merges, your input line that was really shrunk by all the merges will now be expanded all the way back to the original size of the file. And that's what all of this undoing stuff does. All right, so let's move on to part B here. Let me move this guy over here. And let's take a look at part B. Part A. Part B is going to use a regular expression on the input. So what we're going to do is we're going to massage the input a little bit using a regular expression, so that instead of our tokens being just a single byte, or representing by byte pair encoding, a single byte could represent 2 bytes or 3 bytes or 4 bytes or whatever. But what we're going to do in this part is we're going to use a regular expression to first massage our data. And this, by the way, is the regular expression I believe used in Chat GPT-3. Now, if you're not familiar with regular expressions, well, then it's a good opportunity to probably learn about them. You can always pause the video and do a little research on regular expressions. What I discovered is that this regular expression is basically a Perl compatible regular expression. So what I had to do in my coding was I had to use the Perl compatible regular expression library that's available for C to break the input up, to parse it into tokens, and then proceed by merging them using byte pairing. So let's just see how that works. So I have it right here. So if we look at the code here, it's still going to be using the Shakespeare.txt file. And I'm going to use this function I wrote here to get the tokens. Well, if you look at get tokens, do I have that? Or somewhere. Yeah, get tokens right here. Let's take a look at this function here to get the tokens. You'll notice that what I'm doing here is I'm taking in the file. I'm opening up the file here. And I'm basically reading the file into this source here, which is basically the list of all the characters in the file. So it's the character array. And what I do here is I declare the pattern I want to use. If you look at the pattern, by the way, you can see what I'm looking for is I'm looking first of all for in this regular expression. I guess you could call that an apostrophe S, or apostrophe T, apostrophe RE, apostrophe IV, apostrophe M, apostrophe LL, apostrophe D. So these are all, I'm not an English major, so all I can say is, like, for example, a lot of words will end with, for example, apostrophe LL, or apostrophe D, or apostrophe like VE, like I've, I apostrophe VE, I've got problems or something, right? So I'm looking for any words that end with these apostrophe type characters. And then I have an OR here. This vertical bar is an OR. So then I'm looking for here a space followed by a new line. And the question mark says I want, is it 0 or 1 of those? So I'm looking either for a space or a new line, followed by a lowercase or an uppercase letter. 0 or more of these lower uppercase letters. And then again, I have another OR here. So now I'm looking for a space or a new line, followed by some digits, 0 or more digits. And then I'm looking for a space or a new line here, followed by not. This symbol here means not a space, new line, or any of these upper, lowercase, or numbers, digits. So, like, for example, I'm looking for maybe special symbols like a $sign or a hashtag, something like that. Then, of course, I come into this part of the code here, which is difficult to understand and difficult for me to explain. But in essence, what he's trying to do with this is trying to parse the input, so we don't have any tokens or any matches with having a space or end with a space or a new line. So, let's look at this match here and see first what it looks like. Let me bring that up. Where do I have that here? I will go here and I'll go to results. So let's take a look here from the Shakespeare file. We go right up to the top. Remember, the initial size of our Shakespeare file is 1,115,394 bytes. And when you run it through that regular expression, these are the tokens we get. And I've delimited the tokens with hashtags. So if you look at the first token that's matched from the file is going to be the word first. Now the second token that's matched is going to be space citizen. The next token that's matched is going to be a colon. But you notice the fifth token here is going to be a new line, a new line followed by the word before. Because see, my hashtags here will delimit the token. So the next token will be a space followed by the word we, or space followed by the word proceed, space by the word any. So it's basically breaking up all of the input into these tokens. Here's a token that's just a comma all by itself. Here's a token that's space here. Now here's an interesting token here, which is just a new line. Between lines 16 and 17, we just have a new line. The next token after that is a new line followed by the word all, and so on. So you can see it's breaking up this whole thing into tokens. All of the Shakespeare code or Shakespeare file is being broken up into tokens. And if I go all the way down to the bottom here, see lots of tokens. I don't know if I can get to the ending of this mess. Come on, let's go. Boy, oh boy, this is... Well, if I try to do this, I'm gonna overshoot. That's the problem. Actually, you know what I could do is maybe just go back to the bottom, then I could go back up. Might be easier. Of course, anyway, what I've done here is I'm printing out the history file. So let me just. Oh. Boy, really hard to get it right there. I can't get it right there. Anyway, it doesn't matter. Let's go to look what happens here is our table size, our lookup table, instead of being 665, our lookup table is now 15,929. And why is it 15,929? Because we did 600 merges. So our initial lookup table would be 15,329 by 10. But we did that many merges. And of course, the number of parameters went up to almost 5 million. 4,963,000. And if you look at what we've done here is our loss here started at 11.1. And after a bunch of training, we've gone down to 7.5, but this particular run took 57 minutes and 40 seconds, so almost 1 hour just to do this one run. And I didn't do 200,000 iterations in the learning part. I only did, I think I only did 10,000, to be honest. So I did a lot fewer. But let's take a look at some of the code here. And so what we had to do was with this get tokens, I take the file and I run the file through this regular expression here. And you notice I'm using this Perl compatible regular expression functions to compile my pattern here. And then what I do is I go through and extract all of the matches, and each match becomes one token, and I just save all those tokens that I've got. And you notice the tokens are all pointers to pointers. Like it's an array of strings. So each token is going to be one match in the file. Now the other thing you have to know is that in order to use this Perl compatible regular expression, in order to use that, I had to change my make file here to actually use, or in my libraries, I had to include the Perl compatible regular expression library in order to do that parsing for me. So the libraries I use are standard C library, the standard C math library, well, the standard C library of course too, but standard math library, the GSL library, this is a GNU scientific library, and also the Perl compatible regular expression library I had to use. And okay, so if we go through this, just like before, I'm going to do 600 merges here. And what's going to happen is my vocabulary, which is basically my alphabet, is going to keep on growing, and the encoded tokens is going to keep getting smaller. So the number of tokens will decrease. I'll just go through the same thing I did before, basically, with all of my merges. Once I do all of the merges, the rest of this is all very, very similar as before. So I go through the dimensions. I make my initial lookup table here, which is just a random lookup table. But again, it's going to be huge because the length of my vocabulary is now right here, which is almost 16,000. So my lookup table is like almost 16,000 by 10. And I go through again, make my, random B1, W1, W2, B2, gain and bias, running mean, running variable, all this stuff we've done before. And then I go through, and you notice this time I'm only doing 10,000, a loop of 10,000. And this is taking 1 hour on my machine. So the results I get are really, to be honest, pathetic. Worse than useless, because I just doing all this in C is just way too hard for me to do, and since I'm only going through that back propagation through, I'm only going through a couple of layers here. I'm going backwards through the normalization layer, and then I'm going back through the linear layer, the starting linear layer. So my back propagation is really trivial, and yet I still have like 100 lines of code to do that, or more. Okay, and that's about it. So what else is there to say about this file? I mean, I wrote some other sample codes here. Remember, I didn't have to worry about Unicode because the Shakespeare file is all ASCII. But I did work with some Korean characters and things like that, so I wrote little sample C programs to do that. I wrote some hexadecimal to characters and things like that. So you'll see here, I'll upload all of this information here, and you can see it. Shakespeare file. This is basically just a Shakespeare file, shakespeare.txt. So that's it. So this is basically the end of this video number 5, but I want to take a few more minutes just to go over what I've been trying to attempt here. Trying with C to go through some of Andrej's Python code that he goes through. Now he's made a brand new one a few months back called building MakeMore, or building ChatGPT 3 from scratch, which I haven't had a chance to look at yet, but I might look at that and maybe make another video after this one. I'm not sure. But let's just take a few minutes to go over, see what I learned doing this exercise so far. And not to say that I'm done. I may end up with even a 6th video. I'm not sure. But let me go to terminology I learned. So if you look at things, some of the new words I learned doing all of this, I learned about And I'm not going to, and again, no particular order, and I'm not going to go through and explain all of these words, but they all have meaning to me now, like smoothing, one-hot encoding, cross-entropy, log likelihood and negative log likelihood, byte encoding, dimensions, block size, normalization, scale and shift, running mean and running variance, momentum, mini batch, forward pass, backward pass, hidden layer, bias vector, learning rate, loss, embedding, lookup table, gradients, byte pair encoding, merging, tokens, counts and probabilities, activation function, split loss, training, development, and testing data. So these are just some of the key words that I've kind of become a little bit familiar with during my exploration of all of Andrej's videos. And I really strongly urge you to go through his videos. You will learn a lot. The other thing I want to mention just before I finish this is I want to also mention on other things I've learned besides all of those, all the terminology. I didn't realize there was a GNU scientific library for C until I had to use it. I didn't realize there was a Pi GSL interface to the GNU scientific library. I learned more about GNU plot. Initially, I knew I knew about GNU plot, but I didn't know very much about it. Still really don't, but I learned more about it. I learned more about statistics, or refreshed my mind from my college days about mean, standard deviation, and variance. I learned a little bit more about partial derivatives and the chain rule. Again, this is more or less, since I'm retired, I can barely remember any of that stuff from college. So again, I learned a little bit more about linear algebra, like dot and cross products, about Jacobians. I learned about Perl regular expressions. Before doing this, all I knew about basic regular expressions or extended regular expressions, just using them in a bash terminal. But I was totally unaware of the power of Perl regular expressions. And finally, what I learned a lot more about Python and the power of Python, especially PyTorch. So that's it. That's what I've done so far. I will be posting this video soon, and I will post the code onto my GitHub page. And then I'm going to take a little break, and I'm going to watch Andrej's video on building ChatGPT 3 from scratch. And if I have energy and ambition, I might even try to do a video on that. So thank you for watching, and just continue learning as much as you can. Take care. We'll see you next time.